Hello, statisticians. Mr. Youngsaver here from Skew the Script. We're going to analyze a very important topic today, the relationship between police use of force and race. We're looking at data from the Stop and Frisk program out of New York City and analyze it using a chi-square test for independence as well as for homogeneity. Let's skew it. Today's lesson is on chi-squared tests for two-way tables. This is lesson 9.2 in our course sequence. Today we'll be looking at the issue of race and policing. This is a very important and a very charged issue, and we're going to be looking at it at a systemic level using data. Specifically, we're going to ask, is there a relationship statistically between police use of force and race? If you'd like to follow along using our guided notes, you can print it up at this URL from our website. So first we're going to look at the data we're going to look at today and talk about some different tests we're going to do with it. So the data today comes from the Stop and Frisk program. That was a controversial program in New York City that allowed police to stop people on the street and search them for weapons or contraband. We have detailed data on the program from 2003 to 2013. And we can ask of this data, was there racial discrimination during Stop and Frisk? So here we have a random sample of 2011 data from the program as reported by the police officers. And it's organized in a two-way table. This is a table of counts describing two categorical variables where each margin represents one of those variables. So in this case, we have one variable, race of suspects, on one margin and force level used upon those suspects on another margin. And last time we looked at a mock claim from a television commentator who said, police had no force interactions with only 260 white suspects. Meanwhile, a much higher number of black suspects, 1,371, didn't experience force at all. Clearly, black people experience force-free interactions with police more frequently than white people. And we asked, is this a good take? So last time when we looked at this data, we said, let's put aside the raw counts for a second and think about what these mean in terms of proportions. And we wanted to get the conditional distributions. In other words, what percent of people received no force given they were black? What percent received no force given they were white? And so we're going to find the distribution among each racial group. So we can take a look at, say, for example, just the black suspect group. And there were 1,743 black people stopped, and among them, 1,371 had no force to use upon them. So that's 78.7% rate of no force used. And we could do that same type of calculation for each of the force levels. And then we can look at the white suspect group and see among the 308 white suspects stopped, 260 experienced no force, and get the proportions for the rest of them. So now we're doing some apples to apples comparison using proportions rather than raw counts. We can see some meaningful differences here. For example, the proportion of white people who received no force was actually higher than it was among black people. In other words, white people had no force interactions at higher rates than black people. So this television commentator claim, while it might be technically true in some ways, is misleading. It is BS, bad statistics. So last time we looked at this data, we had some lingering questions, and we're going to try and answer those today. First, we're going to look at if there's if the association that we found between police use of force and race is statistically significant, and then we're going to look at some discussion questions. So we're going to analyze this data using a chi-squared test for independence. Question is there convincing evidence of an association between race of suspect and level of force used? We see differing rates in this sample. The question is, are those differing rates different enough to suggest that in the whole population of all people stopped during this program, there was meaningful differences in the level of force used between racial groups? Or if not meaningful differences, differences that couldn't have arisen by chance alone. So we're going to do a significance test for this. We need convincing evidence of it. So the initial idea one might have is to compare proportions using two sample z-tests. And you can compare the proportions, say, for black and Hispanic that receive no force, that receive hands level of force, receive a higher level of force than for black and white, et cetera, et cetera. And if you want to compare all these proportions, you would end up doing 9 hypothesis tests. But that's not a good idea. One, it's just a lot of work to do. And two, you might get a type 1 error because of the problem multiple tests. You always have some chance of getting a type 1 error where you find a statistically significant result by chance alone. And if you keep on doing tests over and over again, you're bound to trip up and find that error. So instead, let's do one overall test. This is the chi-squared test for independence. Here are the hypotheses. The null is going to be that there's no association between race of suspects and level of force used. And the alternative is going to be there is an association between those variables. In this case, it fits into our innocent until proven guilty framework. The null is going to be that force is used at the same rate between all racial groups. And the alternative that we need proof for is that the force is going to be used at different rates between racial groups. So let's go through the logical hypothesis test. Like always, we start by assuming the null is true. So we're going to assume that force is used at the exact same rate between each racial group in the population. And then we're going to say, if in the population, this null is in fact true, how likely is our sample data, that random sample 2011 stops we got? So we're going to compare the distribution of force levels across our sample and see how similar or different they are. And then we're going to draw a conclusion. If different enough, we have evidence that force levels are actually used at different rates between racial groups, and we can reject the null. And if not, we would fail to reject the null. So step one, we're going to assume the null is true. So we're going to use that common refrain in a world where force is used equally across racial groups. So we're going to redo this data and think about the expected counts if there was an equal force rate used between each of these racial groups. So let's break down how we would do that. The overall no force rate in the whole table is simply the total amount of suspects across all groups where no force was used, 2,484, divided by the total of the whole table, 3,164. That's a rate of 78.5%. So if we're assuming the null in a world where force levels of force are used equally across all racial groups, we should see in our data that about 78.5% of suspects from each racial group received no force. So to get these in terms of expected counts with our different sample size for each racial group, we can do a simple multiplication. We need to find 78.5% of the 1,743 black suspects stopped. That's 0.785 times 1,743, and that's about 1,368. We expect 1,368 black suspects to receive no force given how many were stopped. And we can do that for each racial group here. For Hispanic suspects, we get this number. For white suspects, we get this number. And if we want to have a simple formula to do this for all force levels and all racial groups, here is a simple formula for finding those expected counts. You do the row total times the column total divided by the grand total. We essentially did that, but this is just a formula we can use to do it for the rest of them and do it quickly. So in this case, we had for black suspects receiving no force, we look at the row total. The row total was 2,484. We look at the column total. There were total 1,743 black suspects stopped, divided by the grand table total, 3,164, and you get what we got for our expected count, 1,368. So we can do this for the stuff we haven't filled in yet. For example, Hispanic suspects receiving a hands level of force, we can look at the row total times the column total divided by the grand total, we get 1,169. And we do that for all these different groups. So for example, black suspects receiving a gray level of force, we can do row total, column total, and get those numbers. And if you do this for all of those spaces, we can get all of our expected counts. So in this world where force levels are used equally across racial groups, these are the expected counts we expect to get given how many suspects from each race were stopped. So now we're going to take these expected counts and we're going to compare them to the actually observed data from our sample. So here was the actually observed data again. And we're going to look and see how those comparisons match. So white suspects, it looks like, received force less frequently than expected based on expected counts in a world assuming where there is no difference in force level rates between groups. And also they had no force stops more frequently in the observed data than what was expected. Black suspects had force levels pretty close to what was expected. And this makes sense because black suspects made up the bulk of stops from police. So they disproportionately define what is expected in the data set. And Hispanic suspects received force more frequently than expected and had no force interactions less frequently than expected. So now the question is, statistically, are these differences that we see overall large enough to say that they didn't happen by chance alone? So that's where our chi-squared test statistic comes in. Now recall the chi-square test statistic. This is how it works. First, you look at the expected counts and the observed counts and you subtract them to find the difference between what was observed and expected for each table cell. Then we square those differences so that when we add up all those differences together, there's no negatives that cancel things out. We divide by the expected counts to scale what we got by what we expected. And then we add all that up to get a sense of the total differences in this table. So if you want to see the precise derivation of this, you can go back to our last lesson on chi-squared goodness of fit for more detailed explanation. And we know that when chi-squared is big, that means the observed data is very different. Those differences are very large compared to what was expected under the null hypothesis. In that case, your observations, your sample data was unlikely under the assumption the null was true. You'll get a low p-value and you'll reject the null hypothesis. So when the chi-squared value is small, that means that your observed data was very similar to what you expected under the null hypothesis. Those differences in the numerator were small. Therefore, if your null is true, your observations are relatively likely, and you're going to fail to reject the null hypothesis. You don't have convincing evidence against it. So in this case, we had our expected counts and our observed data, and we're going to plug these into our formula for each cell in our table. Let's look at first black, no force. We plug in the observed and the expected counts. We can do that for Hispanic no force as well. And we do a plus, dot, 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 ellipses. It'd be hard to do all these by hand. We actually have calculator steps for this. I'm going to show you what you get in the meantime. If you did all this, you would get 10.17 when you add everything all up. So is this big enough to reject the null, this chi-square test statistic of 10.17? Yes, it is. How do I know that? Well, I'm going to show you during our 4-step process. So let's go through the 4-step process. You're asked a question in FRQ. This is a good way to organize your work such that you get full credit. And so when you're asked, is there convincing evidence of an association? I know I'm going to do a 4-step process for inference. I'm going to do a chi-square test for independence here. So first, you want to state your hypotheses and the significance level. We've written out our hypotheses before, we state them, and then we have an alpha level of 0.05 here. Plan, you want to name the inference method and check conditions. I'm doing a chi-squared test for independence. I'm going to check my conditions. We have these 3 very familiar conditions for us. Random, the data was randomly sampled from 2011 stop and frisk records, so we're good there. 10%, my sample size should be less than 10% of the population size. In this case, my sample size, the 3,164 stops I'm looking at, should be less than 10% of the whole population of all 2011 stop and frisk stops. In this case, there were 685,000 such stops in New York City that year. That's much less than 10%, so we're good there. Large counts, all expected counts would be greater than or equal to 5. Well, it's very hard to get all the expected counts by hand. There's a lot you have to do. There's a good way to do it in your calculator. This is the first set of steps that you can do. As you can try this out, take a pause on the video. The chi-square test will actually be computed by this. And so you can write down this output to save it for later for the do step. And then these last steps here get you the expected counts on the TI-84. So then once you do that, you write down the expected counts and you say, yes, these are all greater than or equal to 5. Now for the do phase, you need to report degrees of freedom as well as your test statistic and p-value. In a two-way table analysis, degrees of freedom is going to be the number of rows in the table -1 times the number of columns in the table -1. When I say rows and columns, I don't mean the total columns, like the totals for the rows, totals for the columns. No, I just mean for the variable values. So in this case, we have 3 columns and 3 rows. I'm going to plug in 3 for each, subtract before multiplying because we're there in parentheses, and then we get 2 times 2, which is 4. So we have 4 degrees of freedom. And the calculator gave us all the rest for the test statistic and the p-value. Now, in order to show my work, I'm going to write in a couple of the chi-squared terms, expected minus observed squared over the expected, just to show that I know my work. But then I'm going to do plus, dot, 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 and I'm going to write in what my calculator gives me, chi-squared of 10.17 with a p-value of 0.038. It's a small p-value. So let's conclude. We have our conclusions template here. And I'm going to say, because our p-value is 0.038, and that is lower than our alpha value of 0.05, we're going to reject the null hypothesis. We have convincing evidence that there is an association between the race of suspects that were stopped and the level of force used against them. So let's compare this really briefly to what we call a chi-square test for homogeneity, and then we're going to get into our discussion questions. Chi-square test for homogeneity is the exact same thing. It's the same thing as a chi-square test for independence, with only 2 key differences. The data is set up a little bit differently, and the hypotheses are going to be a little bit different phrasing. So what we just did is an independent situation. Here's the data set. There are 2 variables, in this case, race of suspect and force level, and they're sampled from one population, stops in New York City. And so these were our null hypotheses. Variable 1 is not associated with variable 2, or they are, and this is what it was like in our context. In a homogeneity situation, the data set is going to be a little bit different. Imagine we did a different study in which we're testing the association between a race of suspects stopped in different cities. So for example, here we have one variable, which is the race of the suspects that police stopped in different cities from multiple different samples from multiple different populations. So we have a sample from New York City, a sample from Boston, and a sample from LA. So this is one variable, the race of the suspects, in 3 different contexts, in 3 different samples. So this is one variable, multiple samples, and this is a homogeneity situation, not an independent situation, homogeneity. The way we write the null and alternative hypothesis here is that there's no difference in the distribution of that variable between groups 1, 2, and 3 of our samples, and there is a difference in the alternative. In this case, that would be there's no difference in the true racial distribution of stops in New York City, Boston, or LA, or alternatively, there is a difference in the true racial distribution of stops in New York City, Boston, or LA. So these tests are very similar. They both deal with two-way tables, and we have the same conditions, math, procedures, etc. So the state plan do conclude to be very similar. The only difference is the data is set up differently, and we're gonna have a differently phrased hypotheses and therefore a differently phrased conclusion when you accept, or sorry, if you reject or fail to reject. So let's go on to our discussion for today. So we found that race of suspect and level of force used were significantly associated. In other words, the differences in use of force rates between racial groups were unlikely to be due to chance alone. And there's a key distinction here between a statistically significant difference and a practically important difference. Statistically significant differences are differences that are too large to arise by chance alone. Our hypothesis test told us that this was the case. The idea of a practically important difference is that there's a difference that is large enough to have real consequences in the world, a real effect on citizens. And descriptive statistics and our experiences tell us this. So I have 2 discussion questions for you. 1, are the differences that we found in force rates across racial groups not only statistically significant, but also practically important? And 2, does our data provide enough evidence to prove that New York police officers are racially biased in terms of their use of force? Why or why not? That's it for today's statisticians. Have a good one.